In this video, we're going to discuss the determination of a limiting reactant in a chemical reaction and the ability to calculate the amount of product formed based on that limiting reactant. This is going to be a follow-up to what we've already done with stoichiometry. If you have not yet watched the video and feel comfortable with stoichiometry calculations, I recommend reviewing that topic first before continuing. Here's a quick run through of the learning objectives in this video. We're going to do a quick review of stoichiometry. Again, this is a stoichiometry based problem. If you cannot do these calculations or are not at least not fresh in your mind, you need to make sure that you go and review that. And we'll hopefully tackle that a little bit in the beginning of the video. We'll then identify what a limiting reactant actually is. It's again just an application. It's a stoichiometry problem with a little bit of a twist. Most importantly, probably in the video, we'll talk about how stoichiometry calculations are going to change. What are you going to do differently now that we're rolling in this idea of limiting reactants? And then finally, as always, we'll wrap up with a little bit of practice. On the bottom right of the screen there, you can see an analogy to this limiting reactant process and the idea of building cars. We'll talk about this analogy a little bit later on and talk about how the number of car bodies and the number of tires is going to fix the amount of product that we can produce. A quick recap of what stoichiometry is all about. It is the ability to mathematically predict the amount of product formed in a chemical reaction based on two things: the balanced chemical reaction itself and the amount of reaction that's actually used. The balanced chemical reaction yields to something called the mole-to-mole ratio. That's the thing that links the amount of one chemical to the amount of other. And the amount of reactant used is the starting value we use in our conversions. And if you recall, these all tend to occupy a very similar and repeatable process here. We always start with this given value, and whatever that is based on the problem itself. The first conversion is always converting to a number of moles. That's only required if the starting number is not in moles. In this case, it's in grams. Our second conversion is always the mole ratio. This comes from the balanced chemical reaction, and our last step, as always, is going to be converting that final answer out of moles to whatever value it is we're looking for. In this case, we wanted to convert it into the number of grams of oxygen that were present. And it's always going to be the same steps, 1, 2, and 3. Step 2 being always present. This is what makes it stoichiometry. And steps 1 and 2 are only needed if you want to work with numbers that are outside of the unit of moles. But this is the general format you should already be familiar with. To start off this process, we're going to take a look at what an original type of stoichiometry problem would actually look like. This is a very classic example. How many grams of ammonia is the product over here, the NH3, would you expect to form by completely reacting 100 grams of N2, so we have 100 grams of this stuff over here, with excess hydrogen gas. And this is how we've always phrased these before with this term excess in here, meaning we've got plenty of hydrogen gas to go around. That means when we run this reaction, eventually it's going to run out of the nitrogen, and we're going to use this entire 100 grams, which means this value is then a very good predicting tool for how much of this is created. We generally do not have a very good idea of how much hydrogen was used, although we could use stoichiometry to figure that out. And this is the part of the problem that's going to change now. I'm not going to be telling you which chemical is in excess anymore. I'm going to change the problems to look like this. You're going to now react 100 grams of nitrogen gas with 25 grams of hydrogen gas. And as a result of that change, now we've got a certain quantity of nitrogen being used and a certain quantity of hydrogen being used. At first glance, it seems like we have tons more nitrogen than we do hydrogen, and that would suggest that the hydrogen would run out first because there's so little of it. But in actuality, that's very difficult to predict. The mass of a hydrogen atom is very much different than the mass of a nitrogen atom, and based on the balanced chemical reaction, we're going to use these at a different rate. The point of all this is we can no longer assume that the full 100 grams of nitrogen is going to be used. It might be the 25 grams of hydrogen that's going to run out first, and as a result, that'll change the context of the problem. We have to add in an extra step to these calculations to first determine which chemical runs out first, and then proceed with the stoichiometry as we've done it before. So let's then define what a limiting reactant is. A limiting reactant is the reaction that runs out first in your chemical reaction. You're going to have one chemical that's limiting, one chemical in excess. Whichever one's limiting is the one that we're going to focus on. By running out of that reactant, the reaction itself is going to stop. If you think back to the way that reactions work, if we've got chemical A plus chemical B reacting to make chemical C, if all of a sudden we're running a reaction, you can imagine at every point in time we're using small amounts of chemical A every time we run the reaction, and we're using small amounts of chemical B every time we run the reaction, and we're creating small amounts of chemical C every time we run the reaction. Eventually, one of these guys is going to run out. We're going to have a moment in time where the last little bit of B has now been consumed and there's no more left. As soon as this happens, the reaction itself necessarily must stop because there's no longer anything for A to react with. And as a result, when this stops, that is the moment we stop creating C as well, and it determines how much product is formed. This limiting reactant, the reason we call it limiting then, kind of following on what I just said, is it limits the amount of product that the reaction can form. The limiting reactant is completely used up. It's the number in the problem that we know has been used, and as a result of that, it's the number that should be used to predict the amount of product formed with stoichiometry. The other reactants, we will describe as non-limiting or excess. We will not use all of these. They have extra of them, and they'll be left over of this chemical in the beaker. Again, typically we don't know how much was used, and as a result, the number you're given in the problem cannot be used to predict the amount of product formed. So one of our jobs in these problems is to identify what the limiting reactant is and what the excess reactants are, because we're going to focus on this one to make our stoichiometric predictions. Let's stop for a moment and take a look at an analogy, as something that might be a little easier to wrap your heads around. We'll talk about the process of putting together cars, and we can think of putting together cars as a chemical reaction. We start over here on the left with car bodies. We're going to take these car bodies and we're going to combine them with car tires, and as a result of that combination, we can create cars. Well, we know that for every one car body that we start with, we're going to need to combine that with 4 cars, and as a result, 4 tires, and as a result, we're going to create 1 car as a result of that. Now, the question is if I have all these resources, this amount of starting material, the question is how many cars am I going to be able to make? Well, the answer to that question is 8 cars. Well, we can make 8 cars. If we think about it, we have 8 car bodies, and we have 48 tires. Now, if we do some math here, we can figure out that based on these tires, we should be able to make 12 cars. The question, though, is we can't actually produce those because once we get to the 8th car being built, we have enough tires to go along, but all of a sudden we're out of car bodies. I would describe the car bodies in this situation as being the limiting reactant, and I would describe the tires as being the excess reactant. This is the amount of product that we're actually able to produce, and this product is predicted solely by the number of car bodies we have, not by the number of tires. And again, what we were able to do here is identify what the limiting reactant is, and then use that limiting reactant in order to predict the amount of product. This is a very simple example, but the idea is going to be the same when we go about doing this with chemistry stuff. Now let's take a look at the same idea, but now with a chemical reaction as opposed to the analogy with cars. We're going to take 2 chemicals, nitrogen and hydrogen, and combine them together to make this product here, which is ammonia. This is a reaction known as the Haber process. It was discovered and actually was one of the reasons we had such an agricultural boom in our country, because this allows for the very rapid and inexpensive production of ammonia, which is a key ingredient in most fertilizers. Now let's talk about the reaction itself. Let's say we start with 6 moles of nitrogen gas, and let's say we start with 6 moles of hydrogen gas, and the question we want to answer is how many moles of ammonia we're going to be able to produce. Now, this is not the way we're normally going to solve these problems, but I think we can talk about this in terms of iterations of reactions. If we run this reaction once, we will end up using 1 mole of nitrogen gas per the balanced chemical reaction, which means we will now have 5 moles of nitrogen gas left. And again, according to the balanced chemical reaction, running the reaction once, we'll use then 3 moles of hydrogen gas, meaning we only have 3 moles of hydrogen gas left. In the process of doing all of that, we will now have created 2 moles of NH3. We can continue the process because we still have both reactants present. If we run this reaction again, we will use another 1 mole of nitrogen gas, and now we're down to 4 moles of nitrogen gas. And if we run this reaction a second time here, we will use 3 more moles of hydrogen gas, and we will now have 0 moles of hydrogen gas left. And again, we will create 2 more moles of ammonia, which means we now have 4 moles of NH3. We go to repeat the process a third time. If we try to run this reaction a third time, we'll use 1 more mole of nitrogen gas, getting us down to 3 more moles. But then all of a sudden we get over here and we realize that we are now out of hydrogen gas, which means this reactant is no longer present. There's nothing left for the nitrogen to react with, so as a result, this reaction would stop. It stopped when we created this 4 moles of ammonia here, and that's the amount of product we would be able to perform or be able to use. As a result, we would describe the hydrogen gas as being limiting. It is the chemical that ran out first, and as a result of running out, it stopped the reaction, and as a result of stopping the reaction, it fixed or determined the amount of product that was being made. Doesn't matter if we have 3 moles of nitrogen left or 30 moles of nitrogen left. The end result is it's just nitrogen in a container by itself. There's nothing for it to react with, and this value over here is actually not very useful for us. There's not a whole lot of calculations we can do with that. So again, just to summarize, we identified hydrogen gas as being limiting by identifying the fact that it ran out first, and based on that limiting value, we were then able to predict the amount of ammonia that was produced. And this is what a limiting reactant problem is. Let's talk about the actual mathematical process that you're going to go for here. The first thing to keep in mind is that limiting reactant, unlike the last problem, limiting reactants typically mean you're doing stoichiometry calculations. And you're going to typically have to do multiple of these calculations in order to get the answer you're looking for. The other important thing to realize is that determining the limiting reactant is not obvious. It might seem like it's obvious in some cases, but in most situations it's actually based on a couple different factors, and determining which factor is the most important one can be a little bit tricky. My message here: do the math. Don't make an estimation based on observations. Let's talk about the actual steps here. You're going to start basically by assuming that each reactant, you're going to give them 2 starting values now. You're going to assume that each reactant is the limiting reactant. And as a result of that, then you're going to choose a product that you want to use to compare the results. You're going to perform a full stoichiometry calculation with each of those starting values, and we have to have a like value to compare to at the end. Now, I very strongly recommend, don't just pick any old product. Typically, in questions in labs, you're going to eventually be asked to determine a certain amount of a certain product. You might as well do your work with that certain product to save yourself steps later. So as I mentioned, once you've identified the 2 reactant starting values, once you've identified the product you're going to compare, you have to do a stoichiometric calculation based on each of those starting values. And as a result, you're going to get 2 different answers from 2 different stoichiometry problems. Now here's the key step. The reactant that yields the least amount of product must have been the reactant that runs out first, and therefore it must have been the limiting reactant. That product is limiting, and the mathematical answer that that calculation yielded is the answer that you're looking for. That's the amount of product that was formed. The other reactant is in excess, and that other answer you got is actually meaningless. I very strongly recommend taking some time, crossing it out so that you don't mistake it for something you can use later on in the process. Now let's go back in the beginning of the presentation and take a look at that problem we started with. We're going to have to determine how many grams of ammonia would I expect to form by completely reacting 100 grams of nitrogen with 25 grams of hydrogen gas. Now we have, if you want to start keeping track of what you're doing here, we have 100.0 grams of this, and we have 25.0 grams of the hydrogen gas. And the question at hand is which one of these is limiting? Hydrogen or nitrogen, which one's going to run out first? And once we know what's limiting, we'll then be able to predict the amount of ammonia that'll be produced. So again, to tackle this kind of a problem, we need to do the full stoichiometry for each. So we're going to start one problem with 100.0 grams of nitrogen, and we're going to start a second problem with 25.0 grams of hydrogen, and we got to set up the full stoichiometry for each one. Just as a quick review, we want to go from grams to moles. There's approximately 28 grams for every 1 mole of N2. The next step is our mole-to-mole ratio. We see from our bounce reaction that for every 1 mole of N2, we're going to get 2 moles of NH3. Now, if you're not sure why I picked NH3, it's because the question asks for an answer that's going to be in a quantity of ammonia. I'm looking ahead and saying, well, if I've got to calculate that later on, I might as well do that calculation now and use ammonia as my tool for prediction. Anyway, that gets us into moles of ammonia, and the last step is going to be convert from moles of ammonia into grams of ammonia. For every 1 mole of NH3, we're going to get a mass somewhere in the vicinity of 17 grams. 1 nitrogen plus 3 hydrogens. And that'll get us a numerical answer. We'll take a look at that in a second. We got to do the same thing all over again with the hydrogen. We have, for example, 2 grams for every 1 mole of H2. We have 3 moles of H2 for every 2 moles of NH3. And then finally, the last step is going to be the same. 1 mole of NH3 is equivalent to 17 grams. Now again, we'll get both answers in a mass of NH3, and that'll allow us to compare how much we got if we started with this versus how many we got if we started with this, and that'll tell us which one of these two is limiting. Take a minute with your calculator, see if you can hammer out some answers with this, and we'll put them up in a second. Hopefully you have some answers down right now by plugging things into your calculator, and we see we get two numerical values. We've determined in this reaction that we would create 121.4 grams of ammonia if we reacted all 100 grams of the nitrogen, and we've determined that we'd create 141.7 grams of ammonia if we reacted all the hydrogen. Well, looking at these two answers, we see that this answer is actually the smaller one, which means that at the very moment, you can imagine again, the reaction is constantly generating more and more ammonia. At the moment we create 121.4 grams, we simultaneously run out of nitrogen gas. Once that nitrogen gas has run out, there's nothing left for the hydrogen to react with, and as a result, the reaction stops. We would never be able to create this 141 grams because there's simply not enough nitrogen around to get the job done. That means for us that nitrogen gas is limiting. We will never use this 25 grams of hydrogen here. We could actually go back up in the problem and replace this with the word excess, and we'd get the same exact answers. And that's basically what we've just determined, is that the hydrogen gas is in excess and the nitrogen gas is the limiting one. Last thing I want to point out before we try another problem is that this again was a non-intuitive answer. We had a lot fewer grams of hydrogen, but because the mass of hydrogen was so light, at the end, the result was that we were using those 25 grams much slower than we were using the 100 grams of nitrogen gas, and as a result, we got answers that were a little non-obvious, I guess is what I'm saying. The point, always do the stoichiometry to determine the limiting reactant. Don't just try and make a guess based on the information you're given and the balanced chemical reaction. I find for most, it's too complicated to do. Let's take a look at another example here. Take a minute on your own to see if you can figure this out. The reaction does require balancing. Once it's balanced, start with each starting value, the copper oxide and the ammonia, the NH3, and determine which one of those two is limiting, and also determine how many grams of the solid copper metal one would expect to form in this reaction. Let's take a quick look at the answers for this problem. Now that we have the balanced chemical reaction, we have our two starting values, our grams of copper oxide and our grams of ammonia. We created two stoichiometry calculations based on these in order to determine which chemical will run out first. Will I use my 61 grams of copper oxide first, or will I use my 15 grams of ammonia? We go through the full stoichiometry calculation. I looked ahead and saw that the problem wanted me to predict the amount of copper metal, so I converted both answers into the grams of copper that they would produce, and I find out that the copper oxide, if completely used, will create 49.1 grams of copper metal, and the ammonia will create 88.0 grams of the copper metal. The lower answer of the two is this answer right here, which means that's the amount of copper metal we'll actually able to produce. When that amount is created, simultaneously we will have used up all of the copper oxide, which means that copper oxide is limiting. Because the copper oxide is now used up, there is nothing left for the ammonia to react with, and the excess ammonia that is left over will stay in the container along with the products that were formed. So again, copper oxide is limiting, and then this is the amount of product we should expect to make. Here's another example of a problem we can take a look at. In this scenario, we have how many liters of carbon dioxide will I expect to form by completely reacting 100.0 liters of propane with excess oxygen gas. And again, we see the reaction below. In this reaction, we're told that we have 100 liters of the propane, and then we have excess of the oxygen gas. And if you think back to previous problems, this actually isn't a limiting reactant problem, because in this situation we are told that we have plenty of oxygen gas by including this term excess. To modify this problem, to make it match more of what we've been working on recently, we would have to change the wording a little bit. And instead of saying excess, we would change it to 100 grams. And again, what I'm trying to do here is highlight the differences between the two types of problems. In a stoichiometry problem, a regular one, you're told which chemical is limiting and which one is in excess. In a problem that's a limiting reactant, you're told the quantities of both chemicals, and you have to determine which one is in excess. So now that we have the problem restructured with our two starting values, and it's now a limiting reactant problem, take a minute, balance a chemical reaction, do your two stoichiometry problems, and see if you can't determine how many liters of carbon dioxide this reaction will produce and which reactant is limiting it. So taking a quick look at the work that we've done for this problem, we were able to identify the fact that we have propane and oxygen gas reacting. We did a stoichiometric calculation where we started with the amount of propane, and a separate problem where we started with the amount of oxygen. We went through the entire stoichiometry process using two different mole-to-mole ratios, one for each comparison of C3H8 to CO2, and one for O2 to CO2. We converted our answers into the desired unit, which in this case is going to be liters of carbon dioxide. This last step actually isn't necessary to identify the limiting reactant, but it is something you typically have to do later. The trick is simply to identify what answer I'm going to need later and make sure you choose that as your comparison. But realistically, as long as you choose one of these two and you have them both in the same answer, you'll be able to compare those results. Anyway, our propane, 100 liters of propane will create 300 liters of carbon dioxide gas. The math actually ended up being very easy here. And our 100 grams of oxygen only produces 42.00 liters of carbon dioxide gas. This is the smaller amount of product, which means when we react these two quantities together, at some point in time, we'll eventually have created exactly 42.00 liters. At that exact moment, the amount of oxygen in the reaction will disappear. There'll be none left, and as a result, there'll be nothing left for the propane to react with, and the reaction will stop. That means this is the correct amount of product being formed in our reaction. This can never happen because there's not enough oxygen gas around for this to burn, which means that our limiting reactant in this case is indeed the oxygen gas. It's the chemical that runs out first, and then the C3H8 will be a chemical that is in excess. Your job right now is to practice some of these problems. It'll give you experience with stoichiometry, and it'll give you experience with limiting reactant problems as well. There are some problems below that you can download and try. Likewise, these problems will get more complicated. There are other steps to this that we can look into. Looking down below, there are other videos that cover some of these ideas, and these are also things we'll talk about in class.